Hello and welcome to Physics Lesson 2.08, Vertical Kinematics, Part 1. In this lesson, which will be in two parts, we're going to look at some of the special considerations that we have to give to acceleration when we are in free fall and how then that applies to problems that we're trying to solve. So for the first third of this, we're going to talk about some of those strange factors that come into play when we're talking about acceleration for an object in free fall. So I'm going to start with some of the most common questions. So let's go with question 1. Why is acceleration due to gravity always down? Well, you guys saw in the lab that we did that once the volleyball left your hands, that from the time it left your hands and it went up, it stopped just its velocity. Well, we'll talk about that in a second. Changes at the very top of the flight path, and we call the vertical path that it travels the flight path. And then it begins to come down and the velocity begins to increase. But you saw that entire time that the acceleration was constant and it didn't change. And that seems odd to us. So what I had mentioned in the previous lab is that acceleration is always down. Why is that? Why does acceleration always act down? Acceleration due to gravity is the result of the force of gravity. I'm going to hit the focus button. I don't know if I can't tell if this is going to be blurry or not. So let's just try to focus this. Might be a little bit better. When we talk about velocity, velocity is changes in displacement. And that can go, if we're starting at our 0 mark and going to a positive 25 or a positive 10, that's going to show up as a positive velocity. We're starting at a larger number and we go towards the negative side, that's going to show up as a negative velocity. But acceleration, and this, to be clear, we're talking about acceleration due to gravity. What I'll see on the first test is that people will start throwing 9.81 meters per second squared in for every acceleration. That's just wrong. We're talking about acceleration specifically due to gravity. And it is the result of the force of gravity. And in the next chapter or two chapters from now, we're going to see that acceleration and force are intrinsically connected. You cannot separate them. And so if a force is always down, the acceleration is always going to be down. The last time I checked, gravity always pulls us towards the earth. If someday in physics people start to levitate out of their chairs because acceleration is pushing you off the earth, we can revise this rule. But due to the nature of gravity, which we'll investigate more and later in the year, it always acts to be attractive between you and the earth. Technically, you're also pulling the earth up, but your mass is so tiny compared to the earth's that we don't notice that. You only notice that you're being pulled toward the earth. So as a result, yes, acceleration due to gravity is always down. It has to be. And let's add that gravity is always attractive. That's not true for some of the other forces we're going to look at. So for example, if you've had a magnet, you know you can use a magnet to either attract another magnet or push another magnet away. So some forces can be attractive or repulsive. Gravity is always attractive. All right, question 2. Is acceleration due to gravity always negative? Well, if it's down, isn't that negative? Doesn't that mean that anytime I work with it, I have to put in negative? And the answer to this is no. The answer is it depends. What does it depend on? It depends on the coordinate system that you pick. There are going to be instances where we're going to want to make down positive, and in that case, our gravity or acceleration due to gravity will be positive, but all the other directions, all the other kinematic vectors that point up will be negative. So if we choose down to be negative, I'm sorry, to be positive, so would acceleration due to gravity. All right, question number 3, the third most common question is, why is the value always 9.81 meters per second squared? Well, the answer is it's not. In fact, there's tables you can look up that give you the values for acceleration due to gravity on spots all over the world. So here's the deal. Let me do the Earth. I'm going to make the Earth blue. So here's my Earth. The mass of the Earth is pretty big. It's a large number. But what we're going to learn about again later in the year is that any object, no matter how massive, even if it's a planet, acts as if all the gravity is centered right at the center of the object, and we call this the center of mass. Gravity is dependent upon the distance between two objects. So if you are walking along Plum Street, this is you. Let's do this in pink. Let's do it in red. So if you're walking along Plum Street, this distance is not going to change. But if you are on Mount Everest, so let's say I'm going to make Mount Everest much larger than, that's Mount Everest on the other side of the world. So if you're on the top of Mount Everest, now your distance from the center of mass has changed. So if you look at this distance to here, let me do it in black. I'm not sure if that's showing up. It is further away. Because it's further away, acceleration due to gravity is actually a little bit weaker. And it turns out on the top of Mount Everest, acceleration due to gravity is 9.78 meters per second squared. So it depends on your elevation. It depends on your elevation. All right, finally, question 4. Is acceleration due to gravity for a falling object ever 0? And this one does have a straight up answer, and the answer is no. AG is constant. And this is why if you put a vacuum chamber, if you take the air out of, if you put a feather and a bouncy ball in a vacuum chamber and you remove the air so that you remove air resistance, you drop those two objects, they will fall at the exact same changing velocities and they'll hit at the same time because acceleration due to gravity is always, in our case at sea level, 9.81 meters per second squared down. It doesn't change. What you're going to be tempted to do, so let's look at me sketch out an object that's being tossed up. So if we have a ball, make it a baseball, and we're going to launch it straight up. It's going to travel up, and then it is going to return. We call this time, we call the pattern that it takes. So from the launch up to the top, down to impact, the flight. So we'll talk about time of flight. What we have here is the top of the flight path. Top of the flight path. And one of the questions you're going to see over and over and over again is for vertical motion. So let's talk about top of the flight path. Top of the flight path vertically. It doesn't matter where I'm at, here, 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 here. AG will always be 9.81 meters per second squared down. But since we're here, let's talk about what happens with velocity. Is velocity ever zero? And the answer to that is yes. Velocity can be zero because what you know is if you launch something, it starts off with a certain velocity, and as I travel up, it gets slower and slower and slower and slower. And what we have here at the top of the flight path is for a split second, just for a split second, our velocity in the vertical becomes zero. And this is a vertical phenomenon. We're going to have to be very careful to keep what happens in the horizontal and the vertical separate. They lead different lives. So right now we're talking about vertical. That's why on a roller coaster or in an elevator, when you have motion like this and you are changing directions, you have that split second where your stomach feels funny. It's because you have an instant, just the briefest instant of zero velocity and you feel weightless. Your stomach and your brain respond to that kind of odd, and it feels like your stomach's dropping. But that's where our brain interprets what's happening in our body. So at the top of a flight path, we're going to have zero velocity, but we're going to have 9.81 meters per second squared down no matter what. I think I'm going to do this in 3 parts instead of 2 because I think we're already about 10 minutes in. And I think it would be easier that way if I have any issues, I can re-record. So again, this is going to be a 3-part lesson. So what are our takeaways here? Why is AG always down? Gravity is always attractive. So takeaway number 1. Is it always negative? No, it depends on your coordinate system. Takeaway number 3, is it always 9.81? No, depends on your elevation. And takeaway number 4, and this may be the most important, are the mechanics of velocity and acceleration for an object in free fall. And I just realized I said for a falling object. Question 4, it should say for an object in free fall. Because remember, even if you're going up, that's still considered to be free fall. Always 9.81 meters per second squared down, but our velocity, we have slowing down and then speeding up. And interestingly enough, just to point out, if I make up positive, I would have a positive velocity here. I would have a negative velocity here, and that would be consistent. I would have a negative acceleration. Because I'm slowing down, I should have opposite signs for velocity and acceleration here. Because I'm speeding up, they should have the same sign. That's kind of a huge factor. So that's just to reinforce. But those are our takeaways for part 1 of vertical kinematics. Thanks for watching, and move on to part 2 at this time.